G'day, I'm James, and welcome to How Round is a Cube. There happens to be a book by that name as well, How Round is a Cube and Other Curious Mathematical Ponderings. I'm not very good at promoting my own material, so there we are, there's a book. Anyhow, it's a collection of essays, and one of my favourite essays in that collection is this one, How Round is a Cube, which is all about the following phenomenon. So imagine the Earth was not round, not a sphere, but was actually a cube. In fact, to show you that this really is the planet Earth, let me just choose a country at random. All right, so here's the idea I once had. So imagine living on this Earth, and you would say the Earth kind of looks flat at most points. In fact, if I lived right here, yep, pretty flat, at least immediately around me, a little small circle around me. In fact, if I drew a circle, like took a rope, pulled it taut, and swung that rope around, I would say within that region, that small region, yes, things look definitely very flat. I'll see a full 360 degrees around me in a nice flat sense. In fact, it's kind of curious that I did the same thing here, stood at this point on an edge, took a rope, pulled it taut, and swung it around. I don't get half a circle over here, and also get half a circle over here. Now, I might notice like a kink in the ground or something, but here's the curious thing. You still see a full 360 degrees of turning around you, at least for a small enough circle. Great! So, full 360 degrees at any point like this on the surface of a face, 360 degrees around any edge point. But these points here are more interesting, these corners, these vertices. Take a piece of string, pull it taut, swing it around you, and make what's the equivalent of a circle, but then you'll notice something very strange is happening. You'll get 90 degrees of turning there, you'll get 90 degrees of turning there, you get 90 degrees of turning there, and that's it. You'll see just 270 degrees of turning. You're missing 90 degrees. You're missing a quarter of a turn. So this actually identifies in some sense that this corner is kind of pointy. It misses a quarter of a turn. This misses no turning, not pointy. This misses no turning, not pointy. That's pointy. In fact, let me define that to be. Let me define the pointiness of a point, P, to be the fraction of turn that's missing from drawing a circle around it. This is missing 90 degrees, it's missing a quarter of a turn. So I'll speak in terms of fractions of a turn. All right, so the pointiness here is actually 0. It's missing no turning. This pointiness here is also 0. But every corner point has pointiness of a quarter. So pointiness of a quarter, pointiness of a quarter, pointiness of a quarter, a quarter, a quarter, a quarter, and the one I can't see also has pointiness of a quarter. Every other point on the surface has pointiness 0. So let me now add up the pointiness of every possible point on this planet. It's going to be mostly zeros, except the total pointiness will be a quarter plus 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 a whole bunch of zeros. That adds up to 8 quarters, which is 2. The total pointiness of a cube, I'm going to say, is 2. Add up the pointers of all possible points, and basically I get 8 quarters, 2. But here's the funny thing. Do it for another polyhedron. Let's just take, say, the tetrahedron, which is made of 4 equilateral triangular faces. Again, imagine standing at some point. If I'm on the actual flat face of a surface, draw a circle around it, a tiny circle, you'll see full 360 degrees. Stand at an edge point, draw a circle around it, like pulling a rope taut, you'll see the full 360 degrees. No turning missing. It's these points, these corners, these vertices that are missing some turning. Pull a rope taut, you'll get a circular arc there, followed by a circular arc there, followed by a circular arc at the back. You say, okay, how much turning did I just see? We saw 60 degrees, 60 degrees, and 60 degrees. You just saw 180 degrees of turning. You're missing another 180 degrees. You're missing half a turn. So we're missing half a turn. I'm going to say the pointiness of that point there is a half. Same reasoning. This has pointiness of a half, pointiness of a half, pointiness of a half. Every other point has pointiness 0. So what's the total pointiness for a tetrahedron? A half plus a half plus a half plus a half. It's 2 again. The total pointiness of a tetrahedron is 2. The total pointiness of a cube is 2. All right, so while I clean the board, because obviously getting a bit messy here because I can't see the camera anymore, is, okay, play with maybe an octahedron, which is 8 triangular faces, sitting 4 sitting on top of a square, and 4 sitting below that square. I'm not drawing a very good picture here. 8 equilateral triangle faces. Work out the pointiness of each point. Every other point is pointiness of 0. Add up the total pointiness, and do you get 2 again? In fact, do it for each of the platonic solids. Do it for an icosahedron, 20 equilateral triangular faces. Do it for a dodecahedron, 12 pentagonal faces. Is the total pointiness always 2? That's a good question. All right, I'm going to clean the board, play with that, pause the video while I clean the board, and we'll be right back for more. Okay, I'm back. Let's now start having some fun. So here's the cube with total pointiness of 2. Quarter, 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 quarter. And let's start shaving off some corners. Let's make it a little bit pointier. So what I'm going to do is I'll do it in a way that I can actually see what's going on, because it gets very hard to keep track of angles. So imagine I took this line that goes from the midpoint of this edge to the midpoint of this edge, so midpoint to midpoint, and then midpoint to midpoint, and then midpoint to midpoint. So there's actual equilateral triangles constructed the same way, though my line should be straight. Yeah, still not much better. And I like shave off that corner. So it's going to look flat here. So hopefully this makes some sense. All right, so there is a shaved cube. What's its total pointiness? Well, again, everything on the face has total pointiness of 0, but pointiness is 0. Pointiness is 0. It's only the corner points that are interesting. And in fact, that one has, nothing's changed, still pointiness of a quarter, pointiness of a quarter, a quarter, a quarter, a quarter, a quarter, and the one behind is a quarter. These ones. Now they're all the same, so they're congruous. So what's going on? Well, that's an equilateral triangle, so I know that's 60 degrees. That's 60 degrees. I also know that I went from midpoint to midpoint, so I actually drew a line like this to shave off. So that's what, 45 degrees, which means the rest of that angle is 135. So that's there is 135 degrees. And that's also 135 degrees, 135 degrees. All right, great. So I know the angles all around that point there. They add up to 135 plus 135, 270, plus 60 degrees is 330 degrees. It only adds up to 330 degrees. I'm missing 30 degrees. But I'm going to think in terms of fractions of a turn. 30 degrees is 1/12 of a turn. So the pointiness here is 1/12. And this is identical, pointiness 1/12, identical 1/12. All right, so what's the total pointiness of this shaved cube? Well, the total pointiness is, well, I've got 7 1/4 still, so 7 1/4, and a 12th plus a 12th plus a 12th plus 3/12. 7 quarters plus 1/4. 7 quarters and 1/4 makes 8 quarters. That's a total pointiness of 2 again. So even if I shave off a corner, the pointiness, total pointiness is still 2. All right, so I'm going to clean the board again. So feel free to pause the video while I clean, but maybe you want to like shave off another corner, do the same sort of way I did here, or just do another type of shaving and try to keep track of the angles and check. Has the total pointiness stayed unchanged? Is it an invariant value of 2? Is it always 2? Try some more shaving and let's see what you figure out. Is it again 2? I'll clean the board and we'll be right back. Okay, working at the pointiness of each point means you need to know the angles around each point, which can be quite awkward to work out. In fact, imagine I had a shape like this, a polyhedron that's full of triangular faces, quadrilateral faces, pentagonal faces, hexagonal faces, maybe 17 diagonal faces, crazy number of faces. It would be a real pain to have to work out each of these individual angles and work out the pointers of each point by going one full turn, take away some of the angles, and then add them all up. So there's got to be a better way to figure out these angles. So let's think about it. Let's think about it. Can we actually compute the total points of something like this without too much work? Well, what were we doing? What were we doing? We were saying, okay, we choose a particular vertex. Maybe I'll choose this one. So the pointers here, the pointers would be, you draw all the angles around it. So it'd be like how much it is around it, add up all the angles around it, and I want the difference from one full turn. So the pointers is 360 degrees minus the sum of the angles around that point. So for example, these add up to 330 degrees around. That means I've got a difference of 30 degrees. 1/12. Oh, I said I want to speak in terms of not full turns, 360 degrees, but literally in terms of full turns, fractions of a turn. So I'm going to express all my angles in terms of fractions of a turn. So not 360 degrees, I'm going to think of one full turn, 360 degrees, minus some of the angles expressed as fractions of a turn. All right, so that's it. So it'll be the pointers of one point. Then I have to do the pointers of another point. It'll be a full turn minus the sum of the angles around. I want that difference, or expressed as fractions of a full turn, and do it again, and do it again, and do it again for all the points on this polyhedron. And I'll do it for all of them, and I'm going to add them up. And the total pointiness would be the sum of all these individual pointinesses, because everywhere else the pointiness is 0. All right. Oh, but think about this. Think about this. I'm going to be doing this for each point, each vertex, each of these corner points on the polyhedron. So I'm going to add 1 and 1 and 1 and 1 and 1 for each vertex. So this is actually first column here adds up to the total number of vertices. Most people call that V. V is the total number of vertices in a polyhedron. And I'm going to be minusing some of all the angles, some of the angles, some of the angles, some of the angles, some of the angles. Let me think about what that sum's going to be. What am I doing? First of all, I'm going to add up all the angles around here, for that one, and then maybe add up all the angles around here for this one, and add up all the angles around here for the next one, and all the angles around here for the next one, and all the angles around here for the next one, and all the angles around here for this one, and all the angles around here for this one, and so on and so on and so on. I don't think you want to watch me do this. This is going to be pretty boring. But in the end, look what's going to happen. I think when I sum up the angles, sum up all the angles around each individual corner, and then add up all those values, I'm just getting every possible angle on the polyhedron. This actually equals all angles. All angles. Whoa! So the total pointiness is V full turns, number of vertices to have that number of full turns, minus the sum of all the angles that I ever see in the whole polyhedron. Okay, now I think there might be a clever way to get to the sum of all the possible angles without having to actually measure each individual one. Because look at this, If I've got a triangular face, I'll get those 3 angles, which I know add to 180. If I've got a quadrilateral face, I'll get those 4 angles, which I know add to 360. So I want to speak in fractions of turn. These add up to 180 degrees, half a turn. These add up to 360 degrees, 1 full turn, 2 halves. Here's a pentagonal one. These ones add up to 540 degrees, 1.5, 3 halves. That's hexagonal, that's pentagonal. Do I have a hexagon in here? No, but hexagon will add up to 4 halves of full turn. Okay, so if I know how many triangular faces I've got, how many quadrilateral faces I've got, how many pentagonal faces I've got, and so on, I can know how many angles on each of those faces. I can then work out the total sum of all the angles. So I need more board space. Let me write this over here. Total pointiness is V minus all angles, sum of all the angles I see. And now I want to start getting at the sum of all the angles by looking at the faces. All right, so what am I going to do? So I need some notation. I need to know how many triangles there are. So let F3 be the number of faces with 3 sides, triangular faces. Let F4 be the number of faces with 4 sides. Let F5 be the number of faces with 5 sides, and so on. All right, so I know each of these gives me 180 degrees, half a turn. So I know the sum of all angles, I will have half a turn for each of those. So if there's F3 of these, I'll have half times F3 of those, 180 degrees times the number of triangles there are. Number of quadrilaterals, I'll have I'll do 2 halves, so just keep it in terms of halves. 1 full turn, 2 halves for each F4 there is, and 3 halves for each F5 there is, and so on, so on. So the sum of all the angles is actually given by that beastly formula. Ugh, what is that formula? Let me take a common factor of a half, because this is really F3 plus 2 F4 plus 3 F5 plus 4 F6 and so on. Ooh, can I make sense of that? All right, so now I'm thinking, okay. I'm really looking at how many faces there are that are triangles, how many that are quadrilaterals, how many pentagons and so forth. And then maybe these things, I've got vertices, I've got faces. In fact, the number of faces, I'll call F be the number of faces, how many triangles there are plus how many quadrilaterals there are, how many there are, is given by this formula. And I've got this weird thing, but think about this. I get a connection now. Vertices, faces, if anyone has any experience with graph theory, you know you want to think edges. So let's think about this. Each of these has 3 edges. Each of these has 4 edges. Each of these has 5 edges. Each of these has 6 edges. So each triangular face has 3 edges, and each quadrilateral face has 4 edges, and each pentagonal face has 5 edges, and so on. So this sum here must be the number of edges. Whoa! Except it's not right, because this edge here gets counted as one of these edges coming from the 3 triangles, also gets counted as one of these guys, one of the edges from a quadrilateral. So this edge actually gets counted twice. This edge gets counted twice as well, as coming from one of these quadrilaterals and one of these pentagons. So actually this is twice the number of edges. Oh, this is looking fabulous. Twice the number of edges. So what have I got here? Okay, twice the number of edges. I'm very close to this one, but this is 3 F3s and only 1 F3, 2 F3s and 4 F4s, 3 F5s and 5 F5s. Okay, so I did say 2 edges minus twice the number of faces, I would then get, what would I get? I'd get 1 F3, 2 F4s, 3 F5s, and so on, which is, there's a half, which is double the number of angles, equals twice all the angles. Oh my goodness, I've got a formula now. All the angles is half of E minus F. Whoa. Okay, this is getting messy, but look what we've just done. The total pointiness The total pointiness of any polyhedron, at least this this bulbous convex one I've got here, is V minus the sum of all the angles, and all the angles is half of E, 2E minus 2F, E minus F. The total pointiness of any polyhedron is V minus E plus F. Whoa. This means this is crazy. This is crazy. It means I never have to actually ever work out any angle I see in a polyhedron to work out its total pointiness. Just work out the number of vertices you've got, count those. How many edges you got? Great. How many faces you got? Brilliant, easy. Just look at the thing and count them, and the total pointiness of this thing is going to be V minus E plus F. Wow, that is a shocker. Not an angle mentioned at all. Now, I have a feeling, I bet I can prove that shaving off a corner some way doesn't change this value, which means it will never change the total pointiness of a shape you've got. Do you think we can do it? You bet we can. But I need to clean the board. Back in a moment. Okay, so the total pointiness of any polyhedron, at least on some great big bulbous convex polyhedron like this one, is given by V minus E plus F, and you have to mention angles at all, which is astounding. Now, what happens when we shave off a corner? Suppose I hone on this corner, just shave it off, or hone on this one, shave it off, or one of these ones. Now, let me just imagine drawing a picture. So I've got some vertex I'm going to shave off. It's got some edges from it. Say it has, I'll do 5 edges coming from it, which means it has 5 faces around it. And then here's its faces, and the rest of the polyhedron just keeps going on. All right, so I'm going to choose 5 around there, but nothing special about 5 here. Now, right now, the total pointiness is given by V minus E plus F. And what I'm going to do is the following. I'm actually going to take this vertex here and shave it off, take a little flat plane, which means I've got 5 faces around it, also got 5 edges around it. I'm actually going to chop off that face there, which is going to create 5 edges this way, like that. And it creates 5 vertices here, 1, 2, 3, 4, 5. Creates a new face, the one in the middle, and it lost a vertex, the one in the middle. So what happened there? So the vertices, I lost the vertex in the middle, so I lost 1 vertex, but I created 5 new vertices. They went up by 5, the number of faces that were surrounding it. So again, nothing special about 5 here, but I just happen to have 5. Edges, what happened to those? Oh, I actually created 5 new edges. I mean, these edges were there beforehand, only these 5 edges are new, so this changed up by 5. Okay, and faces, we created 1 of those, that went up by 1. So V minus E plus F, that changed by 5, negative 1, minus 5, plus 1, that's a net change of 0. This has not changed V minus E plus F, that's still the same value. So the total pointiness of shaving off a corner is exactly the same as the original shape. Shave off a corner, you're not changing the total pointiness. Shave another corner, you haven't changed the total pointiness. In fact, keep shaving corners off of this shape. There's always going to be total pointiness of 2, of 2, of 2, and you'll get a shape that's a billion faces maybe, that's going to look so close to being this shape, this guy, and your eye will not be able to tell the difference. So maybe you could argue in the limit, a cube is just as round as a sphere, because a sphere is just shave, 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 make this rounder, rounder, rounder. The total pointiness is never 2. I'm going to claim the total pointiness is also 2. The whole thing has not changed. Wow, I argue a cube is just as round as a sphere. Crazy, crazy. Now I have made one implicit assumption all through this, that my polyhedra here are connected. They don't have any holes in them. It could be fun to explore, and I'll leave this as an exercise for you. What if I started playing with polyhedra that have holes? For example, consider this polyhedron. It has a big square face with a hole in it, a square hole. And then it's actually going to be really a cube with that hole going all the way through the cube. Do you see what I'm trying to draw there? You can see this hole going through the cube. Wow, so here's a shape with some square faces and, I guess there's like ring-shaped face. If you worry about faces having holes in them, you can actually put in some extra edges if you like. Put an edge there, put an edge there, put an edge there, put an edge there. So actually every face in this figure is actually quadrilateral. Or maybe that doesn't matter. That's worth considering. Do you want those extra edges or not? Anyhow, you still have some vertices, definitely with pointiness to them. And I am wondering, if you worked out the total pointiness of this shape by going back to old methods, look at all the angles around each point and see how far off they are from 360 degrees, though these concave corners could be interesting. This could be fun to figure out. I'm wondering if the total pointiness is still V minus E plus F. Those E's, I'm worried about those E's. Do I need those extra E's or not those extra E's? I wonder. Good things to explore there. I have a feeling you still shave off corners, and this formula doesn't change. Check that. Or I'm wondering if you can also do the reverse of shaving off corners, because these concave regions are kind of awkward. What do you shave off there? Maybe you need to do anti-shaving, like paste in some glue, like a face in that corner there, and actually do the reverse of shaving. So maybe you can build up faces if you like. Does that change this formula? Lots to think about and explore. Because if you do that, I can imagine you can start slowly transforming this to be smoother and smoother and smoother and smoother and smoother and smoother and smoother, like we did for the sphere. Except this time you won't get a sphere from this, you get a sphere with a hole through it. It'll be a donut, a torus. So I'm wondering, a lot to explore here, can you figure out the total pointiness of a donut by beginning with a shape like this and developing a theory that says things don't change to make it smoother and smoother and smoother? That would be amazing. And then could you keep going? Talk about shapes with 2 holes through them or 3 holes through them. Is there a general theory about the total pointiness of shapes with a number of holes through them? That would be astounding if we could figure that out. What great stuff. You're going to say that math is just wild and crazy and truly fabulous. And there's a book, by the way. Thanks so much. This has been jolly good fun. Thank you.